An enterprise data warehouse serves as the centralized brain of a corporation. It's built to process 5 to 10 years of continuous history simultaneously. While a standard transactional database handles daily operations like a single checkout form, a data warehouse is built for online analytical processing. It answers complex, read-heavy historical questions. Instead of logging one new sale, the system calculates total volume across 50 global regions, filtering through a decade of transactions. Processing that much data requires an architecture that contradicts standard computer science practices. The standard rule of database engineering is normalization. It is a design principle used to eliminate duplicate data and save physical disk space. Normalization breaks a single, dense block of data into dozens of lean, interconnected tables to achieve efficiency. But there's a mechanical cost. To answer a massive sales query, the database must execute complex join operations to stitch those separate tables back together. At an enterprise scale, millions of these joins create a massive CPU drain. The system chokes, and business dashboards take hours to load. The design rules that make traditional databases highly efficient are the specific reason analytical warehouses become uselessly slow. To bypass this analytical bottleneck, engineers use a layout called the star schema. At the center of this architecture sits the fact table. It stores the measurable, quantitative numbers, things like revenue, discount rates, and units sold. Radiating outward are the dimension tables. These contain the descriptive text, like regions or item categories, that analysts use to filter the central numbers. Instead of a tangled web, the central facts use direct keys to point to the outer descriptions. This geometry prioritizes the way analysts actually ask questions, allowing for a faster path to the answer. The design of these dimension tables is intentional. They are denormalized. They explicitly embrace repeating, duplicate data. We can see the reason for this redundancy by comparing it to a rival architecture, the snowflake schema. In this diagram, the snowflake schema follows the rules of normalization. It splits its outer tables into secondary subtables to save space, but it increases the number of connecting lines. The star schema does the opposite. It accepts duplicate text, like repeating the same category name a million times, to avoid creating those secondary subtables. This is the great engineering trade-off. The star schema gives up storage efficiency and allows messy redundancy just to keep the join count at an absolute minimum. When a query hits this denormalized star schema, the mechanics are straightforward. The database engine skips the heavy computational lifting. It makes one simple hop from the outer dimension to the central facts. Because the data has been pre-flattened, query execution times drop from hours to milliseconds. Removing that computational friction from the read process is the only way to analyze millions of historical records instantly. This aligns with modern computing economics. Physical hard drive space is now very cheap, while executive time and CPU power remain expensive. The star schema prioritizes expensive CPU power over cheap disk space. It willingly sacrifices one to save the other. Whenever a business leader pulls up a dashboard covering a decade of history, the star schema is likely working behind the scenes. In advanced engineering, sometimes the only way to go fast is to break the rules and be a little bit messy.